Now that we've got the basics of logic sorted, we're going to actually use it to help us talk about proofs. But first we're going to introduce what we mean by a mathematical system, which is actually something you've seen before, but now we can actually formalize this a little bit more. So what is a mathematical system? Well, it's a set or a universe that has some definitions, which are sentences that explain the meaning of concepts that relate to the universe. And a little bit weirdly, any term used in describing the universe itself is said to be undefined. So this seems strange, but we're going to see an example that should make it a bit clearer. Once we know about our universe and our definitions, then we can start having some axioms, which are things that are assumed to be true about the universe that we're working in. And also some rules for how you could create or make more assertions. And then finally we have some theorems, which are the additional assertions mentioned above that we create from the axioms. So this is all very abstract. So there is an example of a mathematical system that you've actually worked with a lot, and that's Euclidean geometry. So Euclidean geometry, our universe consists of points and lines. And although you might not remember, you never actually saw a definition of what a point or a line was. It was kind of assumed that you knew what they were. So those are our undefined terms describing the universe. And then you have some definitions. For example, the definition of parallel lines. And among the axioms is the axiom that two distinct parallel lines never meet. So taking together everything you know about Euclidean geometry, that's a mathematical system based on points and lines. Then you have further definitions, for example, parallel lines or perpendicular lines, and then you have axioms about those various definitions. For example, two distinct parallel lines never meet. And then you went on to create many more theorems, which you learned and could then use to prove more things. Another example of a mathematical system is what we've actually been studying already, propositional calculus. So propositional calculus is the formal name for the logical system that we've been discussing already. Our universe, the set of things we work with, consists of propositions. And the axioms that we've got are the truth tables for the logic operators, and the key definitions are those of equivalence and implication. We use propositions to describe any other mathematical system. Therefore, this is the minimum amount of structure that a mathematical system can have. So going back to our definition of a universe, the axioms of any mathematical system always include this system of propositional logic that we've already developed, because you can't really do maths without it. So that's the idea of a mathematical system, and should give you some understanding of why it is that we decided to go and include logic in this course, because you need it for pretty much anything else that you do. A few more definitions. So you probably remember learning theorems. Well, how do we describe a theorem in terms of propositional calculus? A theorem is a true proposition derived from the axioms of a mathematical system. And we can write it in propositional calculus. So we usually have that a theorem is expressed in terms of a finite number of propositions, so things which we call premises, and then a proposition C called the conclusion. And hopefully, if we use the premises, then we should be able to show that the conclusion is true. So if we write this in propositional calculus, you're assuming that P1 and P2 all the way up to Pn are true, so these are our premises. And therefore, our conclusion, our final proposition, is true. So more informally, we could write this as propositions 1 through n imply C, or if propositions 1 through Pn are true, then C is true. I'm pretty sure that you're familiar with this theorem, if a triangle has a right angle, then the square of the length of the longest side is equal to the sum of the squares of the lengths of the other two sides. So this is Pythagoras' theorem. Let's see if we can write this out. So we have an if a triangle has a right angle. So that's our first premise. Then the square of the length of the longest side is equal to the sum of the squares of the lengths of the other two sides. That's our conclusion. So here we just have one premise, if a triangle has a right angle, and then we can draw this amazing conclusion. So, how do we actually prove a theorem? Well, a proof of a theorem is a finite sequence of logically valid steps, so things using the propositional calculus that we've developed already, that demonstrates that the premises of a theorem imply its conclusion. Now, one of the things that it's important to realize is that there are many different ways of proving things, and there are also many different types of proofs. For example, if we look at Pythagoras' theorem, each of these diagrams leads to a different proof of Pythagoras' theorem, and these are just 3 among hundreds of different ways of proving the theorem. So if you're feeling bored, see if you can figure out proofs for each of these. So as I've just mentioned, we can look at different types of proofs, and we're going to look at 3. In this lecture, we're going to look at direct proofs and indirect proofs. So direct proofs are sometimes called modus ponens arguments, and we'll explain what that means in a bit. And indirect proofs are sometimes called modus tollens arguments. So that's what we're looking at today. And in a couple of lectures' time, we're going to study proof by induction, which is another proof method. So let's start off with direct proofs. So we have a theorem where we have some set of premises. So I'm using a big P to represent all the little premises in our theorem, and our big P implies that some conclusion is true. A direct proof of our conclusion is a way of showing the truth of our conclusion by logical deductions that link our premises and the conclusion. The way you go about a direct proof is you assume that your set of premises is true, and then use logical inference and other logic rules to show that your conclusion is true. So let's look at an example. Suppose that n is an odd integer. Then our claim is that n squared is an odd integer. So there are different ways to prove this. If we want to do a direct proof, then what we need to do is we need to figure out what are our premises, what are our conclusions. So if we have a look at this, our premise is that n is an odd integer. So we just have the one premise. And what we're trying to show is that if our premise is true, then n squared is an odd integer, so that must be our conclusion. So we want to start by assuming that our premise is true, do some logical steps, and hopefully end up showing that our conclusion is true. Okay, so let's begin. Let's assume that P1 is true, so n is an odd integer. Whoops. An odd integer. Now we're going to have to do some mathematical work, and hopefully what we're going to end up with is being able to say, therefore, our conclusion is true. i.e. n squared is an odd integer. So So most of the work actually comes in these steps in between, assuming our premise is true and the conclusion is that our conclusion is true. Alright, so let's think about it. So if we know that n is an odd integer, what do we know? Well, we know that we can write our integer n in a specific way that shows that it's an odd integer. Specifically, we know that we can find some integer k such that we can write n as 2 times k, which gives us an even number, plus 1, which is definitely going to give us an odd number. Okay, and now we want to be able to talk about n squared, so let's see what happens if we square that. So n squared is equal to 2k plus 1 all squared, which is equal to, well, let's multiply out this. So we've got 4k squared plus 4k plus 1. Now if we think about what n squared being odd means, we kind of need to write n squared in a similar way to this. We'd like to write it as 2 times something plus 1, because then we'd know that it was odd. Aha, well, if we have a look at these first two terms, we could take out a common 2. So we could write this as 2 times 2k squared plus 2k plus 1. And now we see we're almost done, because if this thing, this 2k squared plus 2k, is an integer, then we've got 2 times some integer plus 1, and we know that that will be odd. But 2k squared plus 2k is an element of integers, and which we know because we've just multiplied integers together and added them, and integers are closed under multiplication and addition, and letting m equal 2k squared plus 2k, we have that our n squared is equal to 2m plus 1, which is odd. And therefore, our conclusion is true, n squared is an odd integer. So there were different ways that you could have worked through this particular proof, and you might write out different things. But essentially, this is a direct proof because we assumed that n is an odd integer. So we assumed that our premise was true, and then we did a bunch of logical steps, and we proved that the conclusion was true too. Written out in logic, here are 2 different direct proofs of the following. So our first premise is that not P or Q. Our second premise is that S or P is true. And our third premise is that not Q is true. And then our conclusion is going to be S is true. So let's see how this works. So our direct proof says you want to assume that each of your premises is true and use some logical steps to deduce that your conclusion is true. Okay, so our first step says P1 is true. Our second step says that P2 is true. That P3 is true. Our third step uses disjunctive simplification, and you can go and check which those were, to conclude, using P1 and P3 being true, that not P is true. So that's a logical step that's been used. Our step 4 uses our third premise, so this is saying P2 is true. And then finally, our fifth step uses steps 3 and 4 and disjunctive simplification to conclude that our conclusion is true. So if you want to practice your basic logic, here is a second proof of the same theorem, which is this theorem up here, using a different set of logical steps. So what you can do is justify each of these steps. So say when we're using the premise, and if we're using a particular logical rule, what are we using? So the previous two examples both use the following rule of inference, and it's got a Latin name called modus ponens, and this means the mode that affirms by affirming, which sounds a little crazy, but it kind of makes sense when you think about what we actually do when we're using a modus ponens or a direct argument. So our direct argument says, if we assume two things are true, and the two things we assume true are that P implies Q is true and that P is true, then we can conclude that Q is true. And if you think about it in terms of the proof table, it makes sense. So let's think about our truth table. If we've got a P and a Q, and a P implies Q, I'm just going to write out our standard truth table. So we've got 0, 0, 0, 1, 1, 0, 1, 1, and then P implies Q is true in all cases except when our premise is true and our conclusion is not true. Okay, so now, if we're assuming that P implies Q is true, then we must be in one of these cases, because those are the only three cases where P implies Q is true. On the other hand, if we assume that P is true, then of those three cases that we're in, the only one in which P is true is this case over here. And so we can conclude, because we know that we're living in this case over here, since P implies Q is true and P is true, then we can conclude that Q is true. So in terms of a truth table, that's what a direct argument is really doing. As a verbal example, if Claire was born in South Africa, then she is South African. So here we have, if Claire was born in South Africa, so that's our premise, then she is South African, that's our conclusion. Our modus ponens, or direct argument, says we assume that it is true that being born in South Africa implies being South African. And we assume that Claire was born in South Africa, and therefore we can conclude okay, so we're assuming that it's true that if someone's born in South Africa, then they're South African. We assume it's true that they're born in South Africa, and therefore we can conclude that they are South African. A more mathematical example, if x and y are even integers, then x plus y is even. Okay, so we're going to assume that this is true. So we're going to assume that if x and y are even integers, then it is true that x plus y is even. Well, let's see if we can write out a proof. So you might want to take a moment and write out a proof for this, and come back when you're done. Okay, so let's say, so we're going to let x and y be even integers. Then, well, we know that we can write them each as 2 times some other integer, so then we can find, let's say, integers m and n, such that x is equal to 2m and y is equal to 2n. We know that where we want to end up with is that we can write x plus y equal to 2 times some integer. Well, let's add them together. So we've got x plus y is equal to 2m plus 2n, and we can take out a common 2. Aha, but we know that m plus n is an element of integers, so we have m plus n is an element of integers, and just so that we can be clear, let's let q equal m plus n, then x plus y is equal to 2q, so x plus y is even. So the way this proof worked was we assumed that it's true that if x and y are even integers, then x plus y is even, and we assumed that x and y were even integers, and therefore we could prove our conclusion. So that is a direct proof, but sometimes it can be useful to do what's called a proof by contradiction, otherwise known as an indirect proof. And this really uses the key idea that if you prove the contrapositive, it's equivalent to proving P implies Q. So we saw that the truth tables for P implies Q and not Q implies not P are the same. This means that you can use whichever one you like in order to prove something. So our direct proof uses P implies Q, but an indirect proof uses instead that not Q implies not P. So what we're going to do here is we're going to assume that this is true and also that not Q is true, and then we're going to show that not P is true, i.e. that P is false. What does this kind of proof look like? Okay, so we're going to assume that we've got some integer, and we're going to prove that if x squared is even, then x is even. Now you can try and do this with a direct proof, but it's a little tricky. But you'll notice when we do this with an indirect proof, it's much more straightforward. So let's see. So this says our premise is that x squared is even, and our conclusion is that x itself is even. So what we're actually going to prove is that if not our conclusion, then not our premise. So if we write this out in simpler terms, we're going to say if x is not even, then x squared is not even. But hang on a moment, we can actually simplify this a bit more. We can rewrite this as if x is, well, not even means it's odd, then x squared is odd. But we actually just did this proof. So you can go back and check that. So let's have a look at what an indirect proof looks like just written in logical terms. So here's what we want to prove. We want to prove that if you have the premise that says A implies B, and the premise that says not B or C, then your conclusion is that not A is true. Okay, let's see how this proof goes. So remember, our indirect proof is really going to say not C implies not P1 and P2. Okay, so we're saying negation of our conclusion. Now our conclusion says not A. So if we negate that, we get not A, which is A. Now we're using A implies B. So that's our P1. And combining those two together, we get B. B or C is using combining those. This is a premise, and since we have both of those, we get a contradiction. So that gives us an indirect proof of this theorem over here. So just as we had a Latin word for direct proof, we have a Latin term for indirect proofs. This is modus tollens, and it stands for mode that denies by denying. What do we mean by this? We mean that if we assume two things, we assume that P implies Q and not Q are both asserted to be true, then it is the case that not P must be true. Another way of saying that is if P implies Q and Q is false, then P is false. So just to put that more clearly, a modus tollens argument has two premises. It is assuming that P implies Q, which remember is the same as saying not Q implies not P. And it's assuming that Q is not true, and then it's going to show that not P is true, i.e. P is false. So if our watchdog detects an intruder, then it will bark. Another way of saying this in a modus tollens argument is the dog didn't bark, therefore there was no intruder. So it's worthwhile thinking about whether the following arguments are valid. And if they are valid, you can construct a formal proof, and if they aren't valid, explain why not. So let's have a look at these. We've got if wages increase, then there will be inflation. The cost of living will not increase if there is no inflation. Wages will increase, therefore the cost of living will increase. And then our second one, if the races are fixed or the casinos are crooked, then the tourist trade will decline. If tourist trade decreases, then the police will not be happy. The police force is never happy, therefore the races are not fixed. So all of these are using notionally logical steps, but what we want to think about is the conclusion that's reached valid? So give this a try and see if you can explain why they're not valid or write a formal proof if they are. And then in the next lecture, we're going to look at various kinds of validity and invalid arguments.